quantified value of type int. It's again one of those machine ints, so we have to get this guarantee back. So that's currently the specification of this, and the interaction tree continues by just applying this value I to the tree constructor, and it's also contained in the return value. Yep.
Should that key on the left be applied to unit?
Yes, that's sort of hidden in some of the notations that you can define here. I think it's correct. Yeah.
In these examples, the post condition has a reduct of the tree you started out with.
Yes.
Does anything guarantee that, or could you do something else if you're writing a post condition?
I mean, you can in principle put anything here. I mean, the question is then whether the operating system can guarantee what you're specifying here. So that's indeed one thing that is mentioned a couple of slides later, that we're still talking to the Yale folks to see that their interpretation of what this I tree essentially means coincides with ours, so that they can guarantee that only these transitions are possible. But as I said, so of this, what I'm showing here is not the full Linux specification. If you read the man page, then this doesn't fit on probably 10 slides. All right, so what do you do next? Well, you write a little C program. Here split up in 3 parts, 2 small functions and then a main function. Can anybody quickly guess what it does? I know one person who might give us a hint, but well, it reads and writes some stuff, right? So the author of that piece of code, is this what he gave us as an informal spec? It reads a sequence of characters, each in the range 0 to 9, and after each one, and before the next one, prints a decimal representation of their cumulative sum, followed by a new line. We see at least a new line here. And when the cumulative sum is greater or equal to 1,000, or when end of file is reached, then stops. Now, obviously, that specification matches this program, right? And it's obviously also slightly, well, maybe it is precise. We'll see. So what do we do to verify this? Well, you know the principle now. We write a lot of our understanding of this domain of character strings in Galena and define suitable I trees. For example, here for writing not a single value, but writing an entire list of integers, which is just a recursion of the elements of the list and composes the write operations. We may define some additional helper functions that turn characters, turn natural numbers into characters, or turn z's into characters. Then we define maybe a function like this, int r, that gives us a list of integers that we probably want to print in the end, and it does some calculations there with division by 10 and taking things modulo 10 and adding the character representation of 0, I mean like 48 or whatever it is. Int r already suggests that maybe it'll be useful for specifying this function here. It has the same name. It's always a good principle to make such links obvious in your specification. And indeed, here's again our write list and our int r. There's the program again. And then we can write down a specification like this, which claims that this int r function has this behavior. So when you call it with some value I of this particular type and in these bounds, and you will write all the digits that you get by converting this I to a nat and then applying this int r function. Afterwards, you continue with whatever you have. So pretty much the same style as we saw for the OS actions, again, get and put. You will see again here, complex terms and the preconditions, usually somewhat simpler ones in the post conditions, at least what the tree complexity is concerned. And we do the same for the print int function, and maybe also for the main function here. So here we define another auxiliary function, read sum. Again, an I tree, which you see one of the red constructors there, and then we define our overall tree, which has this definition. So it reads something, reads C, and then it calls this read sum with 0 and the difference between Z and character 0 again. And now we can write a specification, which looks like this, which says that the main I tree here is a good precondition, so it describes, it's an upper bound on the interactions that the program will do during its execution. Now, you may be a little bit surprised to see a cofixed point there, because hey, the program terminates, doesn't it? I mean, that's what we said. It should terminate when it reaches 100 or end of file, and there's a return, and there's a break statement there, and but you will actually see it is finite. Here we have the red statement, but of course it needs to be formally infinite because it's an I/O tree. So that's why we need to define it as a cofixed point. All right, and then the fun really starts. We just start firing up the VST and define the usual stuff, the gprocs, the vprocs things, and then we verify lemmas that validate that the individual functions all satisfy their conditions, their specifications. You've done those proofs by now, and you will probably be done after 10 minutes, or maybe you won't be. In particular, with these specifications, you won't be. Can anybody think why? It's maybe not so obvious. So there's a slight mismatch between the way the interaction trees are formally represented and how they behave with a monadic structure, and how we need to access them in the VST proofs. And in particular, we typically don't want to predict in the overall specification how many internal steps, how many of those tau steps the program actually does. But if we really take the I tree literally in the predicates, then we're forced sort of to consume these tau actions somewhere, and we don't really want to do that. So the way to get around this is indeed to modify our definition of the I tree predicate a little bit. We are going to again refer to this has-xed definition of the basic representation of a tree, but we're only going to require that it sort of is satisfied up to the tau transitions that the tree can make. So that's an auxiliary definition that I don't show explicitly here, but essentially removes tau actions from a tree. And then indeed you can not only validate that you still have this property, because clearly T is up to tau equivalent to itself, but also that you can use this equivalence fact to have an entailment between the embeddings of the trees T and T prime into the logic. And that in particular allows us to exploit and reflect in the I tree predicate all those monadic laws that we know are so useful for actually reasoning about interaction trees. And one example of that is that we can actually prove that equiv up to tau, and hence also this I tree implication satisfies the fact that that writing list sort of commutes with the append function of the natural coq lists. So writing two lists in sequence is the same as writing the append of the two lists. And when we make this definition, now it'll only take you 10 minutes to work through all this. All right, so character I/O is now almost solved. Again, we put, so these are the lemmas that we verified, and then we've still got a little bit to do for the top level cleanup to really tie everything together with these external specs that Andrew mentioned yesterday, and then we have an overall theorem that the program satisfies this I-tree. And I mentioned the file where this is all done on some of the slides. You will have to update to the master branch of VST or wait for VST 2.3 because some of these updates were only done in the last 2 weeks. So after 2.2 had been released, and we didn't want to force everybody to once again update just for this talk. Okay, so somebody already mentioned that we will have to eventually link up to Certicos, and this is essentially a to-do list for this. So the challenge is that the semantic models that VST has about C and compilation aren't immediately the same view of the world as Certicos has. Certicos doesn't have this step indexing or these predicates in the heap. But on the other hand, both VST and Certicos agree roughly what language we're talking about, namely CompCert-C. So at that level, we believe we can link up specifications that we make to Certicos. But indeed, how to formally derive this correspondence between these specs is still ongoing work, and one restriction that we may think we may end up with is that this translation will be mostly restricted to communication of first-order data, but perhaps not immediately support all the sort of complex recursive behavior that motivates some of this step indexing. But we'll see. Maybe we can get further. Question up there first.
Do you have plans for them handling lockings? That seems like something where you need some of the higher order properties of the logic and where an OS typically is involved.
Yeah, we have a different style of justifying the rules for locks and other concurrency primitives that are directly related to to how they look in assembly code and on architectures. I guess we didn't talk very much at all here about concurrency in the summer school, so I'm not going to say very much on that. Andrew?
I was going to ask a different version of the same question. When you have an operating system call interface without callbacks, and therefore you have locking operations, it's good that if your client program can be shared memory concurrent, so that it can start a thread in order to do the potentially locking operation. So is that the plan?
So far, we haven't tackled that in particular yet. But yes, how to have these interpretations of trees with concurrency, I think, hasn't also been figured out at the more semantic level. So there's clearly some more work there to be done. Yeah.
So is the choice to use co-inductive data types to model the I/O, is that motivated by a desire to match on the introduction form instead of the elimination form, or is there another technical reason for that?
It's mostly motivated by what works well for the testing and reasoning infrastructure in QuickChik and so. Okay. And that in general you want to be able to specify infinite computations, even though VST currently is just for partial correctness. Okay, let's talk a little bit more about this swap server. So the previous example is essentially a warm-up for our small example of sockets, which still is, of course, a lot smaller than our eventual web server. So we're building really the technology up towards a more realistic server. So this is roughly the way that sockets work in Unix-like systems with a nice picture stolen from the internet, but stolen with attribution. So you can create a socket, then bind it to some ports. You listen for connections, so clients can connect to it. You accept those conditions, and then you can send and receive in both directions. And here are roughly the function prototypes with a little bit of explanations of what they do. And so far, one of those operations is only needed on the client side. And so the idea is now that we repeat roughly the recipe from the previous example on some of these functions. And again, this has been sort of 95% completed, but there's still a little bit of work to be done, actually. So we're going to focus our attention for now on these later operations. Listen, in particular, accept, send, receive, and connect. So here is our type of events, again, of this function, coq level type to type. Uses a couple of particular data as for representing endpoint and connections. And we have events for the typical operations that you see here from the protocol. We haven't done, so in the picture, shutdown is not shown. And I believe we haven't verified anything involving shutdown yet either. But in principle, this sort of, the types here sort of codify what you saw on the previous page in the informal description of what things they roughly take and what the return values of these functions are. All right. Then using some of the type class magic that Benjamin introduced already, we can define slightly more convenient variants of these operations that allow us to embed these network events in any other more general type of events. And that's quite useful because in the end, we don't want to use the network events directly, but what's called here socket events. And they exactly allow us either to do network events or support non-determinism and a notion of failure. So that's currently the way that we build these features into the interaction trees, and it might be interesting to see whether that matches up somehow with how failures in the network then are modeled in systems like Verdi. All right. In addition to maintaining this these network visible interactions, we also need to keep track of the particular status of an individual socket. So we define a second, essentially will be soon, a second separation logic predicate that will keep track of how the sockets themselves evolve over time, rather than the external view of the networks. And this is this ST component, as it will be called in the next slide, will also refer and be applicable to those first operations there that are not visible on the network, but just concern the negotiation between the program and the operating system. The socket state is also updated by some of these actions, but it seemed sensible to us to separate these two roles. So actions that concern the system and its outside world, and from the C program part of the system and the operating system part of the system. All right. So we can then again define our interaction trees in monads, generalizing slightly what we did earlier with the equivalence up to tau. We have a slightly more permissive predicate here now of trace inclusion, but the idea is the same, to support and inject all these monadic rules, such as associativity here into the interaction, the I-tree predicate that we get now over these types of events.